This is section 8.2, and this is on solving systems of two equations with two variables using substitution. So back in 8.1, we did this exact same thing, but we solved it by graphing. That's not always a good option because, I mean, what if your solution isn't like something nice, you know, like 1, 2? What if it's like, I don't know, 25 thirds, 8 and, 1/6? You can't really get that from a graph. The graph is nice though to give you a visual of whether or not you're kind of in the proximity, like in the area. You can graph it and be like, yeah, okay, it's in the first quadrant around that region, so that'll work. So in this one, we're going to use a more algebraic way of solving a system of two equations and two variables. Let's just start off here with this system. Remember, a system is just two equations solved simultaneously. The solution to a system is the intersection point of these two lines. Okay, so I usually put this little brace, this little curly brace over here to denote that we are solving these two equations simultaneously, therefore making it a system. Now, substitution, what it does is exactly what the name says. We're first going to solve one of the equations, it doesn't matter which one, for a variable. It doesn't matter if it's x or y, a or b, doesn't matter. Then plug that into the other equation. The result is going to be one equation with only one variable if you do it correctly. Now you got to be really, really careful because one of the most common mistakes is right here. Most students who make mistakes on this, big mistakes, it's because they accidentally substitute into the same equation. So they forget to substitute into the other one. Now the way these are set up, you can see I've got x plus y equals 6 and y equals 2x. This second equation down here is already solved for a variable. So that first step is already done. So it already is in the form of y equals something. Or it can be x equals something, either one. So because this is already solved for y, I'm going to take this stuff right here, this 2x, because it's the same thing, that's what equals means, this 2x is the same thing as y. So I'm going to replace this y up here with 2x. Sorry, my dog just woke up and is now repositioning for another nap. It's a rough life, isn't it, Lucy? Nope, gotta sneeze first. No, we're lucky at least she didn't decide to clean her butt right now. So we're going to take this 2x quantity and we're going to substitute it right here. So we're going to replace this y with something that is equal to y, and that is this 2x. Okay? So here's what my top equation becomes. Instead of x plus y equals 6, we have x plus, instead of y, we've substituted this 2x in for y. I'm going to use the same color scheme every single time to emphasize, where the substitution is taking place and what it looks like after the substitution is made. So now my top equation becomes x plus y equals 6. And as predicted, this is going to result in one equation with one variable. Now, you guys know what to do with this, right? These are just like terms. That has a coefficient of 1. It's understood to be there. So that becomes 3x equals 6. And because that smushing right there implies multiplication, we're going to undo it by dividing both sides by 3. 6 divided by 3 is 2. That's part of our answer. Remember that when you solve a system of two equations and two variables, you're going to get a point of intersection. That point requires an x and a y value. So don't stop too soon. Now, to find y, to find the other variables, we already found x, to find y, we're going to go back and use that substituting thing. So this part up here where we already had it solved for y, we're going to use that. We're going to plug this answer, so here, let me grab a highlighter. I'm going to use this answer right here of 2, and I'm going to substitute it in for x. Now, you could substitute 2 up here in for x, right? And get 2 plus what gives you 6, and your answer would be 4. That's the beauty of these two being solved simultaneously, is that it doesn't matter which one. However, as we go through more complicated examples, I think you're going to see that going with this one is always going to be the easiest and quickest. So, all right, so I'm going to substitute that answer of 2 into that equation, and I get y equals 4. That means so I just kind of put a box around these because individually these make up my solution. My solution is a point x comma y. So my solution is the point 24. So this is my final answer. So I don't want there to be any confusion that I just kind of boxed these off so that I could find them more easily for my final answer there. All right, so substituting. First, we're going to solve the equation, either one, for a variable, and then plug it into the other equation. And what you should get is one equation with one variable. If you don't, then you've messed up somewhere, okay? All right, so let's look at another example here. All right, so you can already see how I've got it marked off for substitution. We've got one equation is y equals 3x plus 4. The other one's 2y equals 3x plus 5. The top equation is already solved for y. This bottom one, it's close. If I had divided both sides by 2, then it would be solved for y. But this one's already solved for y, so step 1's done for us. Awesome. I'm going to take that expression because that whole stuff is the same thing. That's what equals means. This stuff is the same thing as y. So I'm going to replace this y down here, the other equation, with 3x plus 4. All right, so the bottom equation here becomes, it was 2y equals 3x plus 5, but I replaced y with this expression. Now, just as a little side note over here, this stuff, this whole solving equations and stuff goes really well with the prerequisite sections of 2.4 and 2.5. Those are on equation solving. So if you wanted to do these at the same time, this would be a really good refresher on solving equations. You know, like 1, 2, 3, I think, you know, up to like 5 or 6 step equations. All right, so now solving this equation, I'm going to distribute that 2 throughout there. We get 6x plus 8 equals 3x plus 5. Solving an equation where there's a variable on both sides, we need to move this x to this side. It really doesn't matter. As long as you get your variables on one side, your constants on the other, and then you divide. So I just chose to move my variables to the left. So combining those like terms, 6 minus 3 is 3x. And then moving this constant of positive 8 to the other side by subtracting. So 5 minus 8 is negative 3. So now I've got this equation. Divide both sides by 3, and I get my first part of my answer, x equals negative 1. So if you find that this is a little bit of a struggle and you need a refresher of what's happening right here, 2.4 and 2.5 are awesome to go back to because they're going to have smaller examples to kind of refresh your memory on solving these multi-step equations, okay? All right, so x equals negative 1. Now, what do we do with this? Well, now we go back to the thing that we substituted. So at 3x plus 4, that business right there. And I'm going to substitute this negative 1 into that expression. I know I'm saying the word substitute a lot. All right, so we're going to take that answer of negative 1, and I'm going to put it right there in for x. So see that x right there became negative 1. This is 3 times negative 1 is negative 3, plus 4 is 1. So my final answer is a point. And remember, points always have the form x comma y. So make sure the order is important. It's not just whichever one you solve for first and the second. It's always x comma y. So my final solution here is negative 1 comma 1. That means if you were to graph this equation and you graph this equation, those two lines would intersect at the point negative 1, 1. So that's what it means by solving a system together. All right, so let's look at this next one. Once again, I gave you one where one of the variables is already solved for. This is a good opportunity to pause the video. Now that I've got you set up for substitution, pause the video and see if you can work ahead a step or two or more. Did you pause it? You didn't, did you? You're just going to sit there and watch me do it, aren't you? I know what you're doing. You better pause that video. Okay, so here's what we're going to do. We're going to take this 4x and we're going to substitute it right there in for y. Pay close attention. There's a subtraction right there. So the bottom equation is what's being substituted into. It becomes 4x minus y, which we replaced with 4x, equals 7. Oh, here's where it gets weird. 4x minus 4x, those are like terms. So that becomes 0x. Now, why did I just put 0? Well, it doesn't matter if I put 0 or 0x, right? Because 0x is the same thing as 0. It doesn't matter what x is. It doesn't matter what number x happens to be. It's still going to be 0. So here's what we get. We get 0 equals 7. When these variables subtract off like this, you're going to get those special cases. This is not a true statement. 0 is not 7. If we had gotten 0 equals 0, that's true. But 0 is not 7. So what does it mean if there's not true? It means there's no solution. So what does that translate to as far as the graph of these lines? Well, remember, if there's no solution, if it's an inconsistent system, then that means the lines do not have a point of intersection. These two equations would result in lines that are parallel. They have no point of intersection. So remember, even though I say no solution, Hawks says this is an inconsistent system. So these are parallel lines. So I'll put a little side note over here. So parallel and inconsistent. Just to use the same terminology as Hawks. I don't like that. I think that's a little too formal. I think no solution is a lot more, just kind of, hey, not true. There's no point of intersection. There's no solution. I feel like that one's just a little more clear. But okay. Now, they're going to get a little harder. Because now with example 4, I don't have a variable solved for. So I have to pick one of these equations and solve for a variable. Now, looking at these two equations, 9x plus 3y equals 6, 3x plus y equals 2, I chose, that little double arrow there, I chose to solve this bottom equation for y. Why do you think I chose the bottom equation and chose to solve it for y? Well, I did that because looking at all 4 of these variable terms, it's the only one that has a coefficient of 1. So I knew to solve for that, I wouldn't have to do any division. Whereas if I tried to solve it for x, I would have to subtract over y and then divide by 3 and get fractions and no thanks. So I chose that. So I want to explain that so it doesn't just look all willy-nilly like I just yanked that out of my butt or something. All right, so we get this y. We have that expression, that 2 minus 3x. That just comes from me subtracting 3x. Why did I subtract 3x? Because that's a positive, right? No sign right there. Implies a positive. I'm going to substitute this whole expression right there for y. Now be careful. Don't accidentally substitute it in for x. If you do that, then you're going to get an x and a y together. If you end up with an equation that has both variables, you probably substituted wrong. So it's nice to have those little checks along the way to make sure you're, doing everything that you should be doing. All right, I'm substituting into the top equation. The top equation was 9x plus 3y equals 6. But I replaced y with something that it was equal to. I'm going to distribute that 3. So I get the equation 9x plus 6 minus 9x equals 6. Oh, look at that, 9x minus 9x. Again, those zeroed off. See, just like they did up here, that 4x minus 4x is 0. Here I ended up with, though, 6 equals 6. That's true. Those are the same number. Is 6 equal to 6? Yeah. Is 0 equal to 7? No. right? So that's a true statement. What does that mean? That means that these two lines are the same line. There's an infinite number of solutions. If you graphed those two equations, you would get the same line. Now, remember, Hawkes calls this a dependent system, whereas the no solution is an inconsistent system. Like I said, I really don't like all that formal kind of talk about that. So, it being the same line, where's the point of intersection? It's everywhere on that line, right? So how many points of intersection? They're the same line. They're like, there's one line, and then there's the other one, right? So they're intersecting everywhere. You know, this is just like me, and this is like my youngest son. He's just all over me all the time. Can't get away from him. I'm surprised he hasn't come knocking on the door and busting in to ask me to plunge the toilet or something, else, ridiculously embarrassing. Anyway, moving on. Example 5. You guys don't know how boring this is to just be teaching to nothing, so I'm just entertaining myself here. All right, this one starts to look a lot worse, right? We got these decimals in there. It's okay. We got a calculator. We can do this. So, looking at these two equations, look at those coefficients. Oh, okay, that one's got just like a 1, but it's a -1. Okay, I can handle that. I can work with that. So I took the top equation and I subtracted the 6x over. Now, be careful. That negative is still there. So I got negative y equals 15 minus 6x. So I do have to divide both sides by -1. That does mean I have to divide both of those terms by -1. Okay, so that's why I kind of drew that as a reminder that I have to divide both of those terms by -1, not just one of them. So 15 divided by -1 is -15. -6 divided by -1 is +6. All right, there. Now we've got the top equation solved for a variable, and I'm going to plug that into where? Well, this is where you got to be careful. This is why when you see me write out things like top equation and bottom equation, I'm reminding myself where I started. Okay, if I start with the top equation and I solve it for y, I need to substitute it into the other equation. You don't want to accidentally substitute it back into the equation that you just used. So now, this one came from the top equation, so I'm going to substitute it into the bottom equation. I'm going to replace y with this stuff. All right, and see, make sure you substitute into the other equation. This is, all right, so the bottom equation becomes, it was 0.2x plus 0.5 times y equals 2.1. So we get this, and I realize that this does look like, a hot mess, but that's cool. We can still handle it. No, we're not going to judge it based on how it looks, right? I'm sure it's smart, it's funny. I'm sure it's, your mother's going to love him. It's going to be great, right? Fun at parties, all that stuff. We're not going to judge him based on how he looks. So we're going to distribute that. Now, you can use your calculator to help if you need. The 0.5 times -15 is going to be -7.5. 0.5 times 6 is going to be 3. Remember, that's just a half. That's all 0.5 is. We end up with some like terms, so it's already looking better. We're going to combine those like terms. That's 3 plus 0.2, so that's 3.2x. I'm going to bring down that -7.5, bring down that 2.1. That's a minus, so I'm going to add 7.5 to both sides. Again, you can use your calculator at any point if this starts looking kind of scary and stuff. So I get 3.2x equals 9.6 from adding those together. And then to solve this, because that's multiplication, that's smushing right there, I'm going to divide both sides by 3.2. Remember, you can just use your calculator here. This, I know I wrote it as a fraction, but it really is just 9.6 divided by 3.2. All right, x equals 3. We're not done. That's just part of our answer. But the good news is it's the easy part. Or sorry, this is the hard part. The easy part's still to come. So the rest of it's not going to be too bad. We're now going to take that 3 and we're going to plug it in right here. All right, so I drew this box just to remind you that that's what I'm using. I'm plugging in this answer of 3 into that. So you can use your calculator for this if you want. Just do negative 15 plus 6 times 3, all in the calculator at one point. I just chose to go ahead and multiply that out. So I got y equals 3. It just so happened that both of my answers were the same number. I just wanted to do an example like that that had decimals to it, was a little messier, and ended up with a solution of the same number, because I didn't want you to think, oh, I must have done something wrong if I got the same number twice. Nope, that happens. Okie dokie. All right, now if I'm going too fast, just pause the video and go back. I'm trying to explain everything, but still just kind of keep it moving so this video isn't 2 hours long of me rambling on and on about, you know, how many people cows kill every year or something else, you know, bizarre. Because I could totally do that. All right, so we got 2 equations to solve together. I got another dog behind my chair right now who is just snoring. She is so snarfy. Snoring, snarfy little beagle. So yeah, if you hear that, it's not me. It's her. All right, so this top equation, man, this thing looks like hot garbage, doesn't it? We got fractions, all kinds of stuff happening. And then we got this one. Now, let me tell you what I'm looking at. When I see this and I have to solve for a variable, I'm looking at this x. I see you, x, with your little coefficient of 1. You just look like you want to be solved for. So I'm going to take that bottom equation and I'm going to subtract over 6y from both sides, and that's going to solve this bottom equation for x. Then, because I solved the bottom equation for a variable, I now have to substitute this into the top equation. Now, check it out. I solved for x this time. And the others I've solved for y. Now I'm solving for x. yx, why? Why did I choose x? Because it had that nice coefficient of 1. Right? So that's why I was just like, hey, how's it going? All right, so I'm going to take that expression and I'm going to substitute this right here in for x. That means my top equation becomes x, which I substituted with this red stuff. So this color coding here for your viewing pleasure, this is not just accidental, okay? This is very intentional on my part. This red stuff is all very intentional to help you see where these substitutings are going on. Substitutions? Substitutings, that's not a word. We'll pretend it is. These substitutions that are happening where you can, you know, kind of make those connections and stuff. All right, so because it's all over 3, I'm going to have to divide both of those terms by 3. I'm going to split those up. All right, so let's figure out what's going to happen next, because this is just an equation, but it just looks scarier because of the fractions. But remember, fractions are just division. So 12 divided by 3 is the same as 4. 6 divided by 3 is just 2. So it's not as bad as it looks. Now you'll notice with this one, this y over 5, that I rewrote it as 1/5 y. That's because there's an understood 1 coefficient right there, and I just pulled that coefficient away from that y just to make it a little easier to see. So we've got these two like terms. To make those like terms a little easier to add, I pulled that fraction away. So I have -2 plus 1/5. Use the calculator if you need to add those two together, okay? So when you add those like terms, put a little happy little thought bubble over here, you're going to take -2 plus 1/5, and don't be ashamed if you have to use the calculator on that. Okay? I'd rather use the calculator and get it right than get it wrong. So -2 plus 1/5 gives us -9/5. So there it is, there it is. Moving on. So we combine those like terms here, and I got 9/5. Brought everything else over. I'm going to subtract 4 from both sides, basically getting my variables on one side, my constants on the other. So 1 minus 4 is negative 3. I don't know why that minus 4 ended up so far down here away from it. I don't know, it's doing some nice little physical distancing there. So I get negative 9/5 equals negative 3. Now, here's the thing. When you have a fraction as your coefficient, when you're solving an equation, you can multiply both sides by the reciprocal. So I could have multiplied both sides by negative 5/9. Or, because you have your calculator, you could just say, well, whatever number's in front of that variable, I'm just going to divide both sides by it. So I just divided both sides by negative 9/5. This is the same thing, even though this complex fraction here, this fraction within a fraction looks scary, it's cool. We can just rewrite this fraction bar as a division symbol. So if you use your calculator, you're going to get 5/3. All right, so remember, final answer is going to be an x and a y. So far, all I have is a y. Let's go back to the thing that we substituted. Okay, so remember this from such hits as the previous page. We're going to take this and substitute our answer in for y. That gives me 12 minus 6 times 5/3. Use the calculator for that one. Okay. If you don't want to use the calculator, 3 goes into 6 twice. 2 times 5 is 10. 12 minus 10 is 2. All right, so remember my final answer is x comma y. Get your order straight. Don't put 5/3 comma 2. Don't get all this stuff correct and then go and put them out of order. That would just be so frustrating to miss it, to do everything right and then miss it because you put it in the wrong order. Remember, it's x comma y. There's my x answer. There's my y answer. All right. All right, wrapping up here. One more to go. I know this is kind of a long video, but I've kind of slowed down a little bit for this. All right, word problems. The perimeter of a rectangle is 50 meters. The length is 5 meters longer than the width. Use the equations below to find the dimensions. Okay, there's my equations. The perimeter, remember perimeter is the rim or the edge, so you add up all the sides. Okay, rim as an edge. So here's my two equations. Now the second one, look, it says the length, see that L, is, see the equals, 5 meters longer, that's the plus, than the width. So this sentence in English, the length is 5 meters longer than the width is translated into math for you. All right, the second equation is solved for L. So I'm going to take this stuff right here and I'm going to plug it into the other equation. The top equation then becomes 2L plus 2W equals 50. I'm going to distribute that 2. I'm going to group those like terms. Those 2W plus 2W is going to be 4W. Subtract 10 from both sides. I get 4W equals 40. Divide both sides by 4. We get W equals 10. All right, all you got to do now is take this 10 and go back up here to the thing that you substituted and put 10 right there for W. So the length is 5 plus 10, which is 15. So for this one it said find the dimensions. So when it says dimensions, that's a shortcut for saying the length and the width. So if you see that phrase, but if Hawks just asks you for just the length or just the width, then you don't have to solve for the, for the other one. If it asked for just the width, you could have stopped right there. So, okie dokie. So that does conclude section 8.2 on substitution.